But even without this, there should be restriction.
No, I agree. But like without the positions, they cannot consider restrictions directly.
That's right.
But I suppose it should do it. Not do it. But it's
Okay, so welcome back. So Helmut Schmidt will be talking about uniform effective accounting and mixed Andreo.
Okay, thanks. Yeah, thanks to everyone for coming, and thanks for the organizers, the ones who are here for inviting me. Thanks a lot. It's a great pleasure. Although it was sort of hard to come here, and will be hard to leave as well. Okay, so I'm going to talk sort of about an old school problem, but what I'm really interested in is effectivity. So I think at the beginning of this wonderful conference, Thomas talked about decidability, and so it's structures, and effectivity is sort of goes a bit, I would say, maybe kind of a step further. It says, well, can we provide an algorithm for a given problem to find all the solutions we are interested in? And can we also kind of bound, let's say, the runtime of this algorithm? I mean, in these days you have to use sort of computer science terms. So, okay, what I will talk about, yeah, sorry about that. Yeah. Okay, what I will talk about is the Legendre curve. This will be the well-known object, I would say, pyramid, and yeah, we think about it sort of. Yeah, you can think of this as being embedded in P2, and we have an extra coordinate for the modular part, and lambda is not allowed to be 0 or 1. Okay, so this is a family of elliptic curves over the modular curve y2, which is exactly the one without these 2 points. And our object of study will be the mixed Shimura variety, which is just the Cartesian product of this. And there is a projection down to product of modular curves. And also we will talk about kind of which will be our model of sort of families over products of elliptic curves, more or less, which are isogenic to each other. It's just we take the fibered product. So what is this lambda? So this map here, here, I will just call lambda with so just a descent point like this to its lambda invariance. Okay, and then because yeah, not everyone is kind of familiar with the. I mean, I will bore a lot of people here, but maybe some people are not familiar with the terminology. We call a point on this object special if P is torsion on the fiber over P, the torsion point, and this elliptic curve here is a product of CM curves. Okay, what are CM curves? So usually the endomorphism ring of E is the integers. Sometimes it's bigger, and we will denote by the discriminant of the endomorphism ring of lambda. Okay, so it's usually like an order and some imaginary quadratic field, and it has a discriminant, and this can be sort of thought of as a measure of complexity for this thing. Okay. So I got all this right. Okay, so now we can also define a complexity of a point, which is the order as a torsion point of P in B lambda P to the n. We take the max and the max of the discriminants. Okay. So if we fix this or bound this, then we get a finite list of points in this object. And it's so if you have an effective bound, so if you can compute the bound, we can compute all the points, right? So this talk will be more or less about bounding these kind of complexities, all right, in certain contexts. All right, fantastic. Now, unfortunately, we need to go a bit further with the definition. I apologize. Is also we need a notion of complexity of the special subvarieties of this object. Okay, so let me just say it first in words. So this e to the n is just a group scheme over the base here. And we can have a subgroup scheme, obviously, not necessarily over the same base, can be over like a subvariety here. And if the subvariety if we take a subgroup scheme and the base variety is also special in here, then we have a special subvariety. Okay, so let's be a bit more precise maybe. So a special subvariety. So this is what I like about this object, everything can be more or less explicitly written down, is let's say S in e to the n is a subgroup scheme. And then I will kind of change words. G over some base curve inside e to the n, and B is a special subvariety of y2 to the n. What is a special subvariety of y2 to the n? Subvariety of y2 to the n. It will be more or less of the form, I won't be too precise. P1 up to PR. I should take, yeah, that's a P1. And then we have a bunch of so we'll have a bunch of sort of constant points which correspond to CM elliptic curves, and then a product of modular curves. And the modular curve will be sort of this form. So at least it's complex points. We can write down as lambda t, lambda g1 tau up to lambda g something tau, where gi are matrices in GL2 plus. So just a matrix here with a positive determinant. You can also choose it to have integer entries and so forth. Kind of a well-known story. Yeah.
First, can you change the bank? And second, maybe you want components of subgroup schemes.
Yeah, right. Yeah. You could take components. I'm not. Yeah, you're right. I mean, usually you take components of this. That's true. Components of. But substance. One metaphor to talk too much. Yeah, I'm not sure to which pen I can change. Yeah, I could use another color.
The blue ones work well.
I don't only see green. No, there's a blue one.
The ones on the desk are probably better, good at you.
Yeah.
These ones?
No, the ones on the ones you were taking before, like some.
Aha, yeah, but these were the ones with okay, yeah. I don't know. There's no logic.
No. Maybe it helps if the lights are
Yeah.
because they reflect on the maybe we should
No?
Oh, no.
All right. It's so hard to please everyone. Okay. So.
What's G? G over B?
Right. So S. So a special subvariety S will be a component of a group scheme over some base variety.
Scheme of our special variety.
Yes, exactly. Very well phrased, thank you. Perfect, perfect. So an example would be for such a special, just to imagine something, if we have just a finite group scheme over the base, would be just torsion points, for example. Just assign, let's say, a cyclic group of order n to each. All right. Okay, then, so we can sort of, for each special, we can take sort of the smallest group scheme containing it, and then we can define the complexity. So complexity, so I'm not being too precise here, is the max of the degree of the group scheme over the generic fiber and the complexity of the image of S under this lambda map, so the complexity of the special subvariety of the base. And again, if we fix this, if we bound this, then we can sort of list all the special subvarieties. Okay, so now, of course, Pilar showed that if you take a subvariety y to the n, then I intersect v with the special points. Now on this Shimura variety, and I take the Zariski closure, it is a finite union S. S is special, and we get that the complexity of these special subvarieties is bounded by something, all right? But this something is not effective, so we can't really compute it. We couldn't for several reasons, or nobody could. Right. However, there were some results. I won't be too precise, so it's Kühne and then Pilo Massazanye independently. They proved an effective bound if n is 2. Okay? They could sort of compute the complexity here. And then also Bilo Kühne and some other, for some other special cases that I won't list. And then finally Bignamini, he showed a lot of things, also some special cases in higher dimensions, but it takes kind of a while to state his result. But let me just kind of summarize that he showed if there exists. Oh yeah. Is it here? Is it okay if I finish here? Thanks a lot. Yeah, I should have remembered. So if there exists effective delta and C positive such that we can bound from below the Galois orbit of a special lambda, then basically we can compute an effective thing. But this is, well, depends on which preprint you believe on archive, might be true or not. But yeah, let's say it's still open. But what I will talk about today in the rest of my time is kind of a strategy to say, okay, let's say we have an effective result for some n, then we will have an effective result for e to the n. And the proof strategy we use does not rely on this particular thing, which kind of was the case, let's say, before. So we don't need to know what's happening on the base to kind of deduce that if we can sort of effectively determine the closure, the Zariski of special points, then we can do the same for e to the n. And yeah, so let me just say, make some historical remarks. First, Gao, he proved that the André-Oort conjecture, which I haven't stated, which is more or less this, holds for well, here's how did I, yeah, for e to the n if, let's call this star, if star holds. So if we have Galois orbits on the base, then this holds. Well, we have them in this case, so he proved mixed André-Oort, or the André-Oort conjecture for e to the n. Of course, he has a more general side, which is, yeah, André-Oort for mixed Shimura follows from this guy for Shimura, but I won't state that, just to save time. So if we have a similar lower Galois bound on Shimuras, then it also holds for mixed Shimuras. And his proof strategy was, of course, using the Pila-Saniel method. And his main result was kind of the Axel-Lindemann theorem for mixed structures, with previous results always by Pila and Zimmermann. And I think for the cases he were interested in, and Klingler and Mojafayev. And yeah, but kind of he sort of uniformized the whole e to the n. He took a cover and he applied the usual strategy that Philip talked about in his talks. And I want to talk about sort of a different strategy where we reduce André-Oort for e to the n to just an André-Oort on the base. So we don't need the Galois bounds on the base. This is kind of, yeah. Yeah, sure.
I mean, Pila's case is the one case where I understand the Galois orbit, right? I mean, basically, so what is the issue? What Galois orbit you don't understand? I mean,
For e to the n?
Product of modular surfaces, what's to understand about the Galois group?
For e to the n, for the mixed case?
Yeah.
Yeah, so this, thank you for this question. I will explain that right now. So what Gao actually, well, I wanted to do it a bit later, but say it now. So if, let's say so Gao proved using class field theory, if A is an abelian variety with complex multiplication and field of definition K. So the field of definition of A, we heard about this in this talk about essential dimension. Yeah. So we know what that means. Then T point of order, how did I say? Yeah, let's say n on A. Then he proved that we have a bound of this form. Okay? So basically, let me just emphasize a point here. The remarkable thing here is that it's over K. Okay? That is, then if you combine these two things, the Galois bound of that Pila used and this guy, then you get the Galois bound of the mixed case. And the difference between these two is that this guy is effective. Yeah. Okay, and
So the constant is also independent of AG.
yes, thank you for pointing that out. That's also important. Yes, it's really independent. It's actually, I think, this is what we will use in our proof, and it is a very remarkable fact about the beam varieties. One can do that. And for elliptic curves, there are also some explicit lower bounds by Clark and Vidal.
All right.
All right. So let me phrase it like that. So I will just write BGST because it just takes too much time to write all the names. These are the names I mentioned here plus myself. We have effective bounds for Andreod in e to the n if there are effective bounds for y2 to the n. Or, yeah, Andreod. Y2 to the n. Okay, so I would be a bit more precise right now. And also, we can replace this guy here by e to the n1 cross e to the, well, it should be n. So instead of taking just the Cartesian product of en, we can also take a product of fibered elliptic curves. And here we get, as a corollary of this theorem, we have effective Andreod for e to the m1 cross e to the m2. This follows in combination with the work that I mentioned here for curves. And here I should also mention, before that there was maybe the first theorem in this direction is due to Philip. He proved Andreod for the fiber, just a fiber power of Legendre elliptic curves. And I think his proof, although he doesn't say that it's also effective.
Audrey also had that earlier result.
Andre,
He looked at it.
yeah, I didn't know about that. Okay, yeah. However, the new thing which I will talk about now is that in this particular case, we get bounds that only depend on the degree of the subvariety in here and its field of definition, which I think doesn't follow from the previous results. Okay. All right. Let me just so erase. What's on the board? Oops. I know. Yeah. All right. So, what's the strategy? The strategy is to, so we look at e to the n as kind of, we have y to the n here, and then we have e to the n sort of fibers here. And what we do is, we fix a CM fiber, like this, for the moment, and then we show a very uniform Manin-Mumford for this particular fiber. So really kind of vertically, and that will force the whole family, if you have a subvariety here, let's like this, or V, that will force the special points on the whole V to lie in a special subvariety. So let me explain that. So first state the theorem, GST. So let A be product of CM elliptic curves. And let V in A algebraic subvariety. over some number field L. Okay. And L is a finite extension of K. K is a field of definition of K. Okay. Then we intersect, we just write A tors for the points of finite order of A, and we take the Zariski closure, and this is a finite union. Of torsion translates, so this is the result Philip talked about, is Mannen-Mumford, of torsion translates of connected algebraic subgroups of A, where the order of the torsion is bounded by so the order Ti is bounded by C times and the degree of the subgroups is bounded by the same, and also the number is bounded by the same, where Cm are effectively computable from n. So they only depend on the dimension of A. Okay. So let me just mention so that there are by now uniform bounds on Mannen-Mumford by Gao, Kühne, and others. And however, this result is of a different nature because it doesn't give you a bound on the number of torsion points. This would be just the m. It gives you a bound on the degree and the order, on the complexity. And this kind of result cannot hold in general. It's impossible to hold. Let me just give you an easy example. Let's say you have a multisection from Y2 to E, just a multisection. Then for each n, you can find some lambda Y2 such that S contains S of lambda is torsion of order bigger than n, and moreover, the degree here is bounded in terms of S. Okay. So for each lambda, we can find a torsion point of arbitrary big degree. So kind of even in dimension 0, it can't hold. And sort of with the same kind of reasoning, we can also take sort of a family, let's say Y2 family of curves dominating Y2, and then we can play around with the Betti coordinates. With Betti coordinates, we can show the same kind of phenomenon. Okay, for each order, we can find some fiber of this family such that this curve contains a point of at least this order. The difference is the Cm. So if we allow all fibers, it just can't hold. Okay, it's just not true. Yeah, and there are good reasons for that. As I hope I quickly I could convince you. Okay. All right. So these are the two things. Are there any questions so far? Maybe.
These lower bounds you're using on, maybe not using them, but you said about how much a torsion point increases your yellow. Yeah, this over here. I'm a little confused. How uniform is it in the, so we say field of definition K,
Yeah.
You mean k-field definition in the modular space, for example?
Yeah.
Of the invariant?
Yeah.
And then this depends really only on epsilon, on
Yeah.
nothing else at all? Wow.
Yeah, you can just like,
Oh, this is true. Okay. What can you say like a sentence about the? Is this
Yeah.
based on like Master or is it SIG?
no,
or is
no, it is class view theory. It is
Class view.
basically, if you know the,
Oh, just ideal class groups.
I mean,
you're measuring
the-
how
you-
much they grow.
exactly,
array class
exactly.
groups. I see. Okay.
it is really, so there's your article in fact, and then there's this other one by Olmo and Yafayev, and he kind of just expanded a bit on the technique.
Gotcha.
Well, there was a previous result of Silverberg, but it turned out to be, yeah, I don't know. Well, there's a history, but some results were incorrect and so forth, so I don't want
I
to.
think you just missed the CM. You're saying without CM this is false. You're gonna explain that to us. Yeah, yeah. Well, if
Yeah.
you remove the CM.
If
it's
you
false.
remove CM, and
Okay.
exactly, and just to reinforce the point, it can't hold true.
Okay.
Yeah. So yeah, so because I dreamed of at some point, well, for 5 minutes or so, to get uniform Mann Mumford out of Galois orbits, it's just not possible. You just can't do it. Like directly is. Okay. Okay, so now in the last 30 minutes, I guess, more or less, I can talk to you about strategy. The proof and what goes into it. I apologize, it's a bit technical. But yeah. Yeah, the problem with these effective results is if you want to state what you did, you have to be a bit specific. Okay. Yeah, this is alright. Blue ones are really better. Okay, so what we actually, so let me say something about strategy. So, right. Let's fix x in En. So let me just say again, it's just a product of Legendre curves. And then what we prove is that if you dissect x with special points, then this will be contained in a union of subgroup schemes whose degree is bounded in terms of what I just told you before, more or less, take x to the n. Right. Here we work over Q for the moment. And now, this is not the full mixed Andreola, unfortunately, because what can happen, for example, x could have some, if you project it to y2 to the n, lambda of x is some subvariety in here. Okay? And if we then want to find the special points that lie on the subgroup scheme and on x, so now we kind of, for each such g, we intersect with some x, then the problem is that project to lambda, we get another subvariety in here, and it might have smaller dimension or the same dimension or whatnot. So the problem is you might get something that you then have to apply Andreola, let's say, to kind of find all the fibers where you have a CM point, okay? So we can't get around this fact, unfortunately. We can't beat the Galois problem. Right, I should also say that here the complexity of the subgroups. Sorry?
You mean cosets or just the?
No, it's all torsion. It's a proper subgroup scheme, really nothing really special or something like that. Okay. And so sometimes the dimension is smaller, sometimes the dimension is bigger, but in any case, what you can do is x, dimension of G, the dimension is either smaller than dimension of x, or x is special. And so you can sort of go on by deduction.
Sorry, maybe you said it, but the G's are over special separate.
Yeah.
Okay.
Yeah. G's are over special. So yeah, there will be subgroup schemes over some. Alright, thanks for the question. Okay. So how do we show that? So how do we show that part? So there's one kind of part of it that might be interesting for other purposes. Kind of. And let me just. So how do we show 1? Let's say this is 1. To get 1, we have to prove 2. What is 2? Here I will just simplify to a product, power of an elliptic curve. E has Cn. Okay, just a fixed power we can reduce to this. Let's say to this case. Then we take a subgroup, connected subgroup, algebraic subgroup. Alright, then H, we can imagine H if the codimension, let's say for the moment, is 1. We can imagine H to be sort of cut out by some relation, like this. Okay, where P1, Pn are the coordinates, and alpha I lie in the endomorphism ring of E. Okay. Then if alpha 1, alpha n are in Z, okay, then we can think of H as just being, and we think of A as being some particular fiber in this family. Then we can think of this as just being a fiber of a subgroup scheme that spreads out over the whole base. Okay, we can spread out. H, or at least sort of the base in that case would just be the diagonal on the base. We can sort of reduce to that. Or, as I said, you kind of get these modular curves on the base, so you might have to deal with some isogenies, but I won't get into that. Okay, fantastic, but H is contained in V. Okay, where V, I said, is some. So the setting V is an algebraic subvariety defined over L. And then there are some classical bounds. The ones we found were in by Bompieri and Sanier. We have like the degree of H is bounded polynomially in the degree of V. And then what one would like to do now is to bound the height of these guys in terms of the degree. And this is I would say, kind of a new input. We can show that the maximum is alpha i's is bounded polynomially, actually linearly in the degree of H. Okay, so that says that basically if these alpha i's grow, the degree gets pushed up. Okay, so there were previous bounds in the other direction. This is kind of known, but this direction I didn't know, so yeah, prove it. Okay, but if you have this, then there is another kind of trick that goes into it. Namely, some alpha I is not in Z, then can show that say lambda of E. We get a lower bound on alpha I in terms of the discriminant. It's a very primitive idea, but basically either you had Z or you get some imaginary part that is too big. But if you combine this with this guy, that means that the degree of H is bounded in terms, so you bound the discriminant. Okay? Now all you have to do is find the discriminants, right? So you combine this bound, I see some people are not convinced, you have a lower bound on this, you get an upper bound on big H, and then you use this guy. Okay. And then you get an upper bound of this form. Beautiful. And then if you have this, okay, you can still ask the question, well, can we find these guys effectively and so forth? I said in the beginning one can, and one can in fact bound the field, the degree of field of definition of this guy from below, in fact in terms of delta, but it will be only logarithmically here. So we have effective.
Just like Gauss,
Yeah, it's Gauss and Sagier. Yeah. Did I get? Wait. Yeah, Gauss and Sagier.
oh, so it's not Goldfeld work?
No, I think we found it in Gauss Sagier, but
The lower
You-
bound for class method?
let me.
I thought, yeah.
Oh, really? But I thought well, okay, thanks. I checked that again. Thanks a lot. I'm not familiar with, yeah.
Is it log or log to the 1 minus epsilon?
Say again?
Is it log or log to the 1 minus epsilon?
Ah, yeah, you're right. Yeah, I think it's. Yeah. Well, let's say we have. We only need some delta. Let's say 1/2. Doesn't matter. All right. Yeah, and unfortunately, yeah, this is of course too weak to do the Pilasani strategy, unfortunately, but it's enough kind of for us to kind of find all the points. Okay, then I should say, how do we get and then I should kind of unfortunately I erased it. Yeah. Plastic word. Anyway. Okay, so yeah, maybe we oops. Alright. Yeah. Then how do we get this uniform Money-Mumford for CM elliptic curves? So we have there is some work of Jones and myself where we prove some effective uniform definition of let's say the uniformization map, or you can also just think of Weierstrass elliptic functions. In terms of Pfaffian differential equation, so this was also talked about a lot in this conference. So it's kind of you have your usual uniformization map from C to E. Then you fix some fundamental domain here in, let's say, a clever way. Say something like that, where Tor is the usual thing, and then that gives you an isomorphism down to the elliptic curve in terms of some Weierstrass functions. Okay, and then you can sort of prove that you can this graph, the graph of this function, call it xp, the graph of xp is uniformly and effectively definable in terms of Pfaffian. Pfaffian differential equations. Okay, and then the other thing is that we prove in this paper a counting result, a Pila-Zanje type, Pila-Wilke type counting result for Pfaffian structures that is only depends kind of on the, let's say, complexity of the definition in terms of Pfaffian differential equation. So I won't go into the complexity. It's kind of how many functions you need to define your Pfaffian chain, and what is the degree of the polynomials that appear in the Pfaffian chain, and so forth. And all of this is completely uniform for E, and there's ongoing work to extend this to Abelian varieties. So basically, this would also go should some point go through in general, and the counting result is general I won't say too much about the counting. There are a lot of experts here, but yeah, this is one part, and the other part is obviously the Galois lower bounds by Gao. And we should say for this part we actually use the Pila-Zanje strategy.
To get effective, do you in fact use like mini, or
Sorry, can you repeat?
you need it effective, right?
Yeah.
So do you in fact use Benjamini's sort of refinement, or?
No. Well, what do you mean by Benjamin's? No. That's so the counting result here is for Pfaffian differential equations. Gall has proven stuff for Noetherian differential equations. These are more general than the Pfaffian ones, but the Pfaffian differential equations, they allow you to get a degree of uniformity that you can't get.
Well,
sort of,
looking at effectivity for the Pila-Wilke method is hard, even in the
Oh yeah.
very basic cases.
Well, I didn't say it's easy.
Well, not hard meaning not known.
The hard is also, well, it is known for, so
It's not in this case. Okay.
it's not. It's also, you can basically, if you look at the counting results that Pila and Habiger used, so what I think Philip just talked about, this can be also expressed in terms of Pfaffian differential equations. So this kind of stuff, we hope, will all be effective soon.
Hi, are you talking still about your paper with Jones or about the...
No, the counting is in our new paper. Yeah.
No, but in our new paper actually it's for counting for Pfaffians in general.
But the definition is not effective yet. This is all. Also, I
Yeah,
mean,
so
it's not written down yet
yeah.
for Abelian varieties.
There is a part that you can effectively write Pfaffian definitions for this uniformizing map.
Yeah.
This was in Jones and Schmidt, and this is not fully effective yet. For
It's
Comics multiplication is not used here.
no. So let's say effective Pila-Wilke for unrestricted, let's say Pfaffian structures, or structures defined by unrestricted Pfaffian functions. So Margaret talks about that this year, so I didn't want to go into that. That is also in this paper.
Okay, so you prove a new result.
In this paper,
Effectivized.
in this
Okay,
paper,
okay.
yes. And the other, so there are two parts, I should be more precise. There are two parts. one is the counting. This is as general as you want, as long as you have the Pfaffian. Then there's this other tiny snag, is that you have to also define exactly, and you want it also uniform independently of your beam variety.
Right.
So that is kind of yeah. And this is also something I want to advertise a bit. This Pfaffian stuff is really cool. It is based on Chovansky's theory of binomials and so forth. Yeah.
Sorry, I didn't get this. The definability is for the restriction of the information of the domain.
Yeah, of course. Yeah. You take.
Oh, okay.
You can sort of.
And it has to be the right fundamental domain for it to be.
Yeah. Okay. I can talk about this a bit in the last minute. Yeah. This is also a good point. So you take XP to let's say you just have the lattice 1 Tor, and you sort of take it into to this fundamental domain. All right. Then this guy, the graph of this guy can be expressed in terms of a Pfaffian chain of uniformly bound complexity. However, if you let the Tor vary, then the complexity goes to infinity. So if you choose your fundamental domain stupidly, let's say, you don't get it. But of course you can sort of choose this fundamental domain uniformly for the whole thing. I mean, you just choose it just as I said. In this funny, well, you all know it. Is it towards this? Just a Siegel domain. And of course, there's work of. There were many talks by Petersens and Stachenko who talked exactly about this fact that you kind of need to have a smart fundamental domain. Right, but yeah, I want to advertise. So this is in general. Then we have this other part. Then there's this arithmetic part. We can also get some uniform bounds in other contexts. But maybe actually, yeah. I mean, there's lunch soon, right? So let me just finish with one kind of curious problem that I just want people to be interested in. Let's take. We have a lot of effective results in Andreort now. Andreort type, mixed Andreort, and other things. But effective is sometimes a bit. It's not satisfying because, like, can you actually give me the solution set, right? I mean, like, I fix some variety. Give me the solution set, please. We would need some sort of super quantum computer for that with these kind of methods. But let me just give you kind of a neat sort of problem, and which I want to pose as a challenge. Maybe someone can do it. So let's say we fix that, and then we just fix x to be x naught in Q bar, let's say. We just fix x naught. Can you determine is torsion? Sorry, but I want to determine torsion on E lambda, and E lambda has Cm. So with the Galois-Lower bounds that I just talked about from Gross, Sage, Goldfeld probably, you should be able to. This is an effective problem. You can basically compute some bounds and you have a list. But can you actually, this most simple case, can someone do a program that could return the list? Even, let's say, Z starting with Z or something like that. This is still open. So I just wanted to maybe, to finish up my talk, just wanted to emphasize that yeah, we have proven many beautiful theorems and Andriot and so forth, but the problem of effectivity is still very much open, and even like explicit results are super rare. So yeah, I think I stop here. Thanks. Any questions?
Can you say a word about this complexity of differential equations?
Yeah, sure.
Just like, what kind of thing is it, and why do you need this fundamental domain? Does it relate to the same kind of?
So basically, the way you do it is you actually take. Let me write it. So you have.
Can you say first, like, how it's defined? Like, what do you mean by complexity of the Pfaffian differential equation?
Right. So. Yeah. So firstly, differential means you have some function, some chain. Function f1 up to fr, and sort of the partial derivatives of fi should be kind of polynomials in the previous ones, minus 1. And as was pointed out, if you do that, for example, for the sine function, which you can do with the addition theorems, you get some poles.
Which function?
For the sine function, sine of x.
Oh yeah.
You can do that, but it's very beautiful. You get a poles, which forces you to restrict to an interval. Right, but otherwise the theory works quite well, and you bound the degree of these polynomials and the length of this chain. And the way you do it is you don't look at this guy, but you look at the inverse, and you have elliptic integrals. Okay, and basically the inverse of this is more or less given like that. But if you differentiate that, that's an algebraic function. So that means you can find sort of a Pfaffian chain for that.
But it all looks very algebraic. I don't understand why the fundamental domain you choose would matter, or where tau would matter for this kind of thing. For you
So
just care about degree.
the other thing is the other thing is you need to. So this guy, as you well know, has monodromy, right? So, but in order for this Pfaffian stuff to work, the functions, the Pfaffian functions, it's not just that they have to satisfy this, they have to be defined on nice domains. Okay. So what you do is, you have like let's say you have your 0, 1 here, and then you kind of do branch cuts.
It's
right?
about like the number of branch cuts.
Exactly. Well, no, the branch cuts is fine, but then like as you kind of take this guy, the inverse, you take the inverse, and then you sort of might swirl around. And you might have many fundamentals domain to cover. So this is what you have to do. Yeah.
So it's deeply related to this like period domain landing
Yes.
in finitely many fundamental domains kind of thing.
Yes,
the same
it's
kind of-
exactly kind of effectively getting
okay.
the hold of that. Yeah. Yeah. Thanks for the question.
Other questions?
Yeah. Go.
Yeah, so I thought you said somewhere, what happens if you replace elliptic curves by abelian varieties?
Yeah.
So suppose you had this definition.
Yeah.
Does that thing with the lower bound work?
I haven't figured it out yet, but I don't see why not. The proof that this works is incredibly simple, but you need some. I think it should work. Yes, but I haven't written it down yet. So.
I should have thought about it myself. Because I'm a...
But you can't. Yeah, I mean.
Would you maybe some quick follow-up? That's okay. This you're proving some sort of like if you map you get definable fundamental domains. If you sort of take some branch cuts in your variety, how generally can you do this? Can you do this like for an arbitrary? I don't know.
So we did it for
family
these.
of varieties?
We did it for elliptic curves, and as I said, there is some ongoing work on the beam varieties. We haven't expanded that yet further. Yeah.
But in principle, if just like any family of varieties.
Well, you need some ideas, to do
You
it.
do?
It's not completely. So this guy, I mean, was like literally writing down. I mean, you can also like. There's a proof. Well, we also did it for semi-abelian, where you have kind of extra fundamental domain problems. So you can do all that. We actually get a bound of 42 fundamental domains. Completely uniform. But like, you have to, I just didn't, I never followed up on this. Yeah, but it's,
One shorter.
perhaps.